Thank you for the introduction. So today I'd like to tell you about microfluidics from the broader field to our team's focus. And so the talk is kind of divided up into two areas. One is a fairly general introduction and overview of microfluidics through the ages, from the 70s through to now. And then oh, it's going to talk to?
No. Oh, that's not going to.
That right? Okay, good. So, so the beginning will be an introduction to microfluidics, and then I'll look about the work that we're doing at the University of Alberta at Team Microfluidics, for which I'm project manager. So, microfluidics, what is it? There are a number of ways that, number of terms that are used to describe it that are more or less synonymous. Lab on a chip, LOC, miniaturized total or micro total analysis systems. Is this mic working? Can you guys hear?
That was for the recording.
Oh, very good. Okay. So really, what is microfluidics? It's meant to convert the many steps involved in an analytical procedure in a lab, in a conventional lab, into one chip. And so, as you might imagine, there are a number of advantages that you can reap by putting all these things together. You can get speed of analysis in some cases just by virtue of miniaturizing, by shrinking down the sizes of these different operations. Because they've now been shrunk, you can put lots of different, lots of the same analyses right beside each other in parallel and run multiple samples at once, or run the same sample for multiple analyses at once. Reduced sample consumption is an important point in a lot of places where your sample is derived from a patient, or it's very expensive, or both. Improved performance by virtue of miniaturization. Sometimes some of these operations that you're doing, such as capillary electrophoresis, have better performance just because the dimensions are smaller. And one of the biggest ones, especially from a product development perspective or an industrial perspective, is reduced operator interaction. That means that your product arguably has legs. Your product now is one thing that does a whole lot. The operator hopefully just pushes go at the start after they put in the drop of blood or urine or whatever the sample may be in a medical setting, and a whole bunch of operations ensue. Maybe they go and have a coffee and come back in 15 minutes and the results are ready. So that can be very attractive. Let's look at the history of microfluidics, because it began quite a while ago and had a big lull. The first example of microfluidics really is Steve Terry in 1975 for his thesis, published in 1979 as a paper in IEEE. I apologize for this picture. I actually wrote Dr. Terry to see if I could get a version that you can see, but this is all that you can pull from the journal online. Really what it is, the block diagram here shows you that you've got a capillary column to do the gas chromatography, and he's got an embedded detector. This is the miniaturized part of the system, all on this one chip right here, and you can vaguely make out a circular form here, and that is the GC column through which the different components separate. That was miles ahead of its time. There was a lull of 15 years before new work started up, basically with Andreas Mantz first up in 1990, in the late 80s as well, with in his postdoc in Japan. But the first publications really came out in 1990 with Andreas. Lars Mattsson, this is actually a new one to me. I just discovered this while preparing this talk in 91 in Sweden, and Jed Harrison, who also worked with Andreas Mantz in the early 90s. And shortly thereafter, Michael Ramsey's group, then at Oak Ridge, did a lot of work exploring a lot of areas. And so here we have examples of some early chips. This is a piece of glass that is etched to provide channels, and you inject different compounds into these channels and then run them down a long channel to effect the separation of the components inside that sample. And here's the layout of their chip. Here's an example. This is from Jed Harrison's group. This is another example of there's the outline of the chip, and here's what happens when you fill it with a fluorophore, something that fluoresces. And the idea is that you inject it at this intersection right here and drive the sample down, and you can see what begins as one plug separates out into two, and that's because they have two fluorescent dye specimens in their sample. As we move on into the 90s, we have research expanding in all sorts of directions, really. So I've listed a few here: pre and post column reactions, fluidic manipulations to be quantitative and measured, serial and parallel sample manipulations, different kinds of materials developed for to provide the stationary phase, a place to rest for liquid chromatography, LC, porous materials for high surface area, DNA sequencing. This chip right here is one developed by Rich Matthews' group at UC Berkeley. This is the 96 capillary version where they're doing their sample injection right here. There's the a blow up of the sample injection, and you've got a capillary, 2 capillaries for each one of these units, and then you drive the separation down, and detection happens close to the center. So the detection system spins underneath and monitors that whole chip all at once. And he's got a 384 version channel DNA sequencer version of this chip too. This is actually an example of an LC and CEC, both methods of separation, chemical separation, device that was pioneered in Fred Renier's lab and made here at Microline for Fred Renier. And this came out in 1998 and is a really nice example of what you can do with the high control that you have with microfabrication. In this case, this device I think was made in quartz. Here are a couple of nice examples, again in the 90s, of really well-controlled fluidic manipulations. And the ones on the right here come from Mike Ramsey's group, and the top image shows the layout, and the bottom image shows that layout in use for doing sample dilution in a parallel form. And he's also got a serial diluter. On the left, we've got one example of a mixer. There are probably a dozen different designs that have been explored for microfluidic mixing. You're actually trying to do something that the technology isn't great for. One of the things about microfluidics is you've shrunk everything down, so now you have everything flowing in a laminar regime, and mixing is not easy to do because things kind of stay to themselves. The only thing that's helping you is small diffusion distances. So what he's done is, with these tread marks on the bottoms of the channel, he's induced flows going in different directions, and so things are kind of forced to wrap in around themselves, and then you have small diffusion distances, and eventually you wind up getting very good mixing. These are sections, confocal micrographs taken where the dotted lines here. I don't know if you can make that out, but it's a nice example of how do you both use the features of microfabrication to get around some of the limitations. Here are a couple of videos, and videos are always fun, especially if they work. Let's hope that this actually works. I got these all from Andreas Mantz, who was one of the pioneers, and so we've got a few examples done, I think mostly in the late 90s. And this one here in the top left, we're going to see a parallel injection. Please tell me that's still running. Yes, it is. Okay. Oh, you can't see it. Okay, hold on. I got one more trick here. Let's go back. Let's see if... Okay, here we go. Yeah, I love technology too. Here we go, you get the video. So, what's happening here is he's moving, and that's, you can see there's actually a little bit of leakage going on as he finishes the injection. But nonetheless, that's one of the earlier examples of a highly parallel injection scheme. Okay, so let's try this one.